Vector operations in R to the fourth. Let us have this example wherein U, which is equal to 2, negative 1, 5, 0, and V equal to 4, 3, 1, negative 1, and W equal to negative 6, 2, 0, 3 be the vectors in R to the fourth. We're going to find X using each equation. So for the vector X, it is equal to 2U minus the quantity V plus 3W. So we apply distributive property. So that would be negative V minus 3W. 2 times 2 negative 1, 5, 0 minus V. So that's 4, 3, 1, negative 1 minus 3 times negative 6, 2, 0, 3. So take note of these values, and as we go to the next slide, that would be equal to 2 times 2 negative 1, 5, 0. So that's 4, negative 2, 10, and 0. And then we copy 4, 3, 1, negative 1. And then we distribute 3. So 3 times negative 6 is negative 18. 3 times 2 is 6. And 3 times 3 is 9. Now we're going to have the operation 4 minus 4. So that's 0. 4 minus 4 is 0 minus negative 18. So that's positive 18. Second term, second coordinate. Negative 2 plus 3 is positive 1. 1 minus 6. So again, negative 2 minus 3, sorry. So that would be negative 2 minus 3 is negative 5. Negative 5 minus 6 is negative 11. 10 minus 1 is 9. 9 minus 0 is 9. And then 0 minus negative 1. So that's positive 1. 0 minus negative 1 is positive 1 minus 9. So that's negative 8. So this is the vector X. Another one using vector addition. So we're going to solve for X if we are given with 3 times X plus W is equal to 2 times U minus V plus X. We can combine terms involving X. So that would be 3X for this one. And then we transpose this to the other side. So 3 times W. So that's minus 3W on the other side. 2U minus V. And then we transpose this on the other side. So the result would be 3x minus x. And then we have 2u minus v minus 3w. 3x minus x is 2x. So when we are solving for x, it would just be, we divide everything by 2. So 2u minus v minus 3w all over 2. We plug in the values of u, v, and w such that the result would be 1/2 of 18, negative 11, 9, and negative 8. So if we're now going to distribute the 1/2, it would be 9, negative 1/2, 9 over 2, negative 4. Theorem 4.3, Properties of Additive Identity and Additive Inverse. Let V be a vector in R raised to n, and let C be a scalar. Then the property below are true. The additive identity is unique. That is, V plus U is equal to V. Since V goes back to the original value V, so U is 0. So that's the additive identity, the number that you add to the vector V, which would result into the vector V. So no changes in the value for V. So that's the additive identity. The additive inverse of V is unique. So the number to be added to the vector U is the vector V such that U plus V is equal to 0. So the additive inverse of U is negative V, and negative V is the additive inverse. So we designate negative V as the additive inverse of the vector U. We also have the 0 vector 0 such that 0 times v, a scalar 0 multiplied to the vector v would give us the 0 vector. Another property, any constant times the 0 vector should be 0, the 0 vector itself. If constant times v is equal to the 0 vector, then either the constant c is 0 or the vector is the 0 vector. The additive inverse of v is equal to the vector v itself. Linear combination of vectors. An important type of problem in linear algebra involves writing one vector x as the sum of scalar multiples of the other vectors v1, v2, and vn. That is, for the scalars c1, c2 up to cn, then x is equal to c1, v1 plus c2, v2 plus and so on and so forth until cn, vn. The vector x is called the linear combination of the vectors v1, v2, and v sub n. So you have the vector v1, v2, and vn. You get a constant multiple of this vector and that would result into your vector x. So that is your linear combination. If the applications of this would be our printer, you can produce any color you want. If you have a complete tank of ink, the CMYK, cyan, magenta, and yellow, if you have these colors, you can produce any color possible. So you're just going to mix these three colors to form another vector, which is a vector of color. So let us have this problem. Let x be equal to -1, -2, -2, and the vectors u, v, and w as stated. So u is equal to 0, 1, 4, v is -1, 1, 2, and w be equal to 3, 1, 2 in R cube. Find the scalars a, b, and c such that au plus bv plus cw is equal to x. We're going to apply matrix equality such that the vector x, which is -1, -2, -2, is equal to the constant multiple au plus bv plus cw. Applying that, we distribute 0a minus b plus 3c. So 0a minus b plus 3c. 1a plus b plus c. So a plus b plus c. That is equal to -2. 4a plus 2b plus 2c. So 4a plus 2b plus 2c equal to the third component. So taking note that -b plus 3c is equal to -1, a plus b plus c is equal to 2, and 4a plus 2b plus 2c is equal to -2, we are going to have 4a plus 2b plus 2c is equal to -2. That is equation 3. For equation 2, we multiply it by 2, so you have 2a plus 2b plus 2c is equal to -4. So that would cancel this out, and then we do subtraction. So 4a minus 2a is equal to 2a. -2 minus -4 is +2, so a is 1. With a being equal to 1, so we can have equation 3. 4 times 1 plus 2b plus 2c is equal to -2. So we have b 2b plus 2c equal to -2 minus 4, -6. So b plus c is -3. We also have -b plus 3c equal to -1. So if we're going to add this, it would be 4c equal to negative 4. So C is indeed negative 1. From this one, B is equal to 3C plus 1. 3C, 3 times negative 1 is negative 3 plus 1. It is negative 2. So thus we have X equal to AU, so 1U, minus BV, so minus 2V, plus CZ, plus CW, so plus negative 1W. So that's all for this meeting. Thank you, everyone.